Systems built on shared responsibility are everywhere, but they contain a hidden vulnerability, a specific way they can break down that is often completely invisible. Today, we're going to examine that precise mechanism of failure. Let's begin with an assumption that feels like common sense. When a task is really critical, what's the standard move? You add more people, more eyes on the problem, more hands on deck. It just feels more secure. That's the intuitive model. But the reality of the system is often the exact opposite. As you add more responsible parties, the probability that any single one of them will act can actually go down. You've probably experienced this. A group project has one critical file that needs to be submitted. Everyone knows it's due, everyone has access to it, and yet the deadline passes and the file is never sent. Why? Well, it's because each person assumed someone else would handle it. The failure had nothing to do with capability. It was a structural breakdown in responsibility itself. So to really understand how this happens, we need a model. We'll start by looking at how these systems appear on the surface, which is often just an illusion of stability. Imagine a heavy block suspended in midair. It's being held up by several ropes, and each rope is held by a different person. At a glance, the system looks not just stable, but redundant. The objective is simple: keep the block from falling, and it appears completely secure. Let's just quickly define the components here. The block itself represents the collective goal, the shared outcome everyone is working toward. Gravity is that constant downward pressure, the risk of failure that is always present. And the agents? Well, those are the individuals holding the ropes, the responsible parties. For the system to remain stable, the physics are straightforward. The total upward force from all the agents must equal the downward pressure of gravity. That's equilibrium. But this model is incomplete. It only describes the system at the collective level, and it completely ignores a powerful set of incentives acting on each individual agent. So let's add that layer. This is where we uncover the fundamental tension between what the system needs as a whole and what each individual is incentivized to do. This is the core mechanism of diffusion. So you have two opposing forces. On one side, the collective requirement is clear. Everyone needs to maintain that upward force. But on the other side, each agent has their own local rationale incentive to minimize their personal energy expenditure. And it's crucial to understand this isn't about laziness or malice. From an individual's perspective, it's a perfectly logical optimization. This inherent conflict gives rise to a phenomenon known as responsibility diffusion. The definition is simple. It's the process by which an agent's feeling of personal obligation goes down as the number of other agents goes up. You could almost think of it as a kind of simple mental math. An agent's perceived accountability is roughly equal to 1 divided by the number of people involved. If you are the only one holding the rope, you feel 100% accountable. But if there are 10 of you, your share of the accountability drops to just 10%. And this leads us to the most counterintuitive part of this whole mechanism. The greatest risk to the system isn't that one agent will dramatically fail or just let go of their rope. That's actually quite rare. The real hidden danger is that every agent, acting rationally, decides to hold on just a little less. It's this quiet accumulation of small, rational decisions that begins to silently erode the stability of the entire system. So let's watch how this invisible risk begins to build up. Let's put some numbers on our model. Let's say that holding the block stable requires a total upward force of 95%, but the system was designed with a 5% safety margin to handle unexpected shocks. So right now, the total pull is 100%. The system looks healthy, it has a buffer. Now, an agent makes that rational, local optimization we talked about. They see all the other agents pulling, so they ease their own effort by just 1%. The total pull drops to 99%. Visibly, nothing happens. The block doesn't move. But that invisible safety margin has just shrunk to 4%. Then, another agent makes the exact same calculation. They observe the system is still stable, and they too reduce their effort slightly. Again, no alarms go off. The block remains suspended. But the collective safety margin has quietly eroded even further, now down to 3%. What's happening here is a coordination failure. Each agent is making a perfectly reasonable decision based on the information they have locally. They assume the rest of the system can absorb their small optimization. The problem is, every other agent is making the same assumption, and the system's resilience is silently being consumed. To make this concrete, think of a safety report that has to pass through 5 different departments. Each team, assuming the others are being extremely rigorous, simplifies their own checks just a bit to save resources. Any single one of those decisions is defensible, but the cumulative effect is a final report where no one has performed a truly thorough review. This slow erosion of the safety margin continues until the system reaches its final state, a breakdown that appears to come from nowhere with no single identifiable cause. It's an emergent property of the system structure. Eventually, the sum of these tiny rational optimizations completely depletes the safety margin. The next agent who reduces their effort, even slightly, causes the total upward pull to dip below the force of gravity. The threshold is crossed. The state change is now irreversible. And after the failure, if you try to find the root cause, you won't find a single one. No one agent is to blame. No single decision was the mistake. The failure emerged as the predictable outcome of all those rational choices interacting within the system. And this brings us to the final core insight. This type of system doesn't fail because its agents behave irrationally. It fails because its agents behave too rationally, optimizing for their local conditions within a structure that doesn't align their individual incentives with the collective outcome.